That's about it.
See what I have here? Interested?
Always bring the interesting things to talk about.
This, my friend, what do you think?
I don't know. What is it?
So it's potato starch inside. Same volume, like half a liter in here, and in here, same amount of potato starch.
Okay.
So it's like resembling a bioreactor.
Okay.
Where the potato starch is the cells.
Okay. So you have two different shapes of a bioreactor.
Yep.
Right. And you want to see what with you have the same volume in both of your vessels, but they're different shapes.
Yes. But I think it would be very difficult for you to sell these things, right?
As what? As
a harvest device.
Yeah, I think vessels like this wouldn't necessarily do well in the market. You're right.
Well, even if they're single use and even if they're sterile and everything, they have the surface area is just way too small, right? So it'll take forever.
Well, there have been people who have tried to just let the bioreactor finish running and just have the gravity settling take place inside the bioreactor itself, and then decant the material off the top. But it's not very efficient.
No, it'll take you days for the cells up here to go all the way down, right? Instead at the bottom. And also, they will not be very dry. You lose a lot of, the protein, what you're after is inside around the cells. It's in the liquid. And the liquid will not be totally clean.
No, you don't get a very efficient separation. If the goal, coming out of the bioreactor is to separate the product-rich liquid stream from a concentrated cell suspension where the cells have already done their work and now we need to move downstream with the liquid, you're right. You'll lose a lot of the product-rich liquid if you just count on gravity separation like this.
Right. So I guess this is what we're going to spend the next, 20, 30 minutes on. More or less, discussing how things settle, how you can make it single use, and what we did to transfer our 140 years of knowledge in stainless steel separators to a plastic version of a separator. And I'd also like to bring up, I would like to say thank you. Thank you, Doug.
You're welcome, Pontus.
No, but so we were sort of sparring partners for 5 years, right? I was the R&D guy. You were the sales director or the marketing director or something. And we had the same goal. We need to develop a single-use separator based on these principles and make sure that the customers got something that was useful for them.
Yeah, I would agree with that. We didn't always see eye to eye in terms of the things which were most important, or perhaps the execution, choices in the execution of the product or the design of the product, in terms of providing a benefit to solve a particular problem for customers. So, yeah.
And my point is just that's perfectly normal. That happens in every company. But now that we both have sort of different roles, I just want to, this is my way of saying thank you. It's been a pleasure the past 5 years. I really enjoyed working with you. I don't think I've said that, especially not on tape. But let's get into what did we achieve?
Yeah, because I think you're right. The proof is in the pudding, right?
Yes.
We can have disagreements along the way, but at the end of the day, if we can, point to what's been done and, have people recognize it for the success that it has been.
Of course.
I think that's the icing on the cake. Yeah.
Pudding. You said pudding.
Icing on the cake.
But bring up the pudding then. You said this is the pudding, right?
Proof is in the pudding.
Yeah,
icing on the cake.
This is the proof. This is the pudding.
You can have your choice of good English phrases.
I don't have icing on my pudding. So what is it? Tell me.
Well, this is a plastic execution of one of our core technologies. This is a plastic execution of a disc stack separator,
right?
Which has long been used in biopharma industry. As long as that particular process duty has been around, we have been in the business with it with a stainless steel version.
Right.
But a lot of customers have moved to a single-use production platform for some of these various products. And for many, many years, the only thing that was available to them was depth filtration.
Yeah.
And so we had a lot of requests to say, well, can't we bring this efficient separation method into a single-use format?
Yeah.
And it had a lot of technical challenges.
But for a long time, we tried to tell them, no, just buy a stainless steel, it's better, right? Just keep it in there. Why do you really need all this plastic instead?
Well, I think that was an easy thing for us to say because there were a lot of technical problems that hadn't been solved. We didn't have any alternative. But it got to the point that developing the alternative was an absolute requirement in order to provide customers what they so desperately needed in a single-use production environment.
It would be great if we could have had some more potato starch at this point, right? Because what's happening is that these customers, the ones who are desperate, is because they have too many cells in their bioreactor, right?
Well, that's true, right? When you say too many, though, I mean, that was done quite on purpose. Right, each cell can produce, only so much of the target proteins, and if you're interested in getting the maximum production out of a given size facility, the answer is more cells.
Right,
more cells equals more product, but it also equals a lot of problems when it comes to the downstream processing.
Right, because a filter, if you have 1 or 2 or 5% maybe, you can use a filter percent cells in your liquid. The filter works fine.
Yeah, because it's manageable from the idea that a filtration system has a certain capacity per unit area, and at low cell concentrations, you're right, that works just fine.
Yeah. But when you get up to like 10 or 15 or more, then it's just too much for this system to separate.
When you talk about 10 or 15, you're talking about percentage volume of the cells. Sure.
The packed cell volume. When you're done. So this is where the separators come in, and that's how I think that the history books will be written. People started developing single-use centrifuges once there was an economical incentive to do it. You have more cells, now you will need a separator because the filters will not do the job forever.
Yeah, I think that the request had come to us for a lot of years before we were able to solve some of the technical problems.
Right.
So if it's a question of which came first, I think the demand came before we were ready to address the issues.
Right.
And it was quite a set of technical challenges in order to come up with something that would get the job done and still be translatable back to the legacy product in stainless steel in terms of scalability backwards and forwards.
Right. And maybe we should point out then for those who have never seen this, that this is replacing, let's go back to the area first, right? So this is a small bioreactor, it takes forever to sediment. If you make the area larger, now it goes faster because the particle is at the top of the liquid, only travels a short distance. So if you pour this one into a football field, well, it'll settle in a few seconds. And this football field is what's condensed into this machine.
That allows you to get the job done very quickly at a throughput which matches the processing needs in this particular step.
So if you have a bioreactor, 2,000 liters, you leave it settling for, 2 days, or you run it through here in 2 hours?
A matter of minutes, right? Your retention time across a sedimentation device, which uses both an increased surface area and a higher gravitational force, right?
Yeah.
Because here, we're of course operating under 1G.
Yeah.
And if we start to rotate something like this at several thousand RPM, we get several thousand times gravity working for us here.
Right.
So that combination of the increased surface area and the increased relative G-force in the device is what gives you something which is an equivalent settling area of a football field.
Yeah. So here's the football field. And if you've never seen a football field condensed into this format, this is where you connect it to your bioreactor, where the cells are making their drugs. They get in here, and the cells are heavier than the liquid, so they're transported through gravity to the periphery, and then being transported out through this tube, which we call the heavy phase, right? And before, somebody's probably wondering, how do you get the football field in here, right? And you said the gravity, or the RPM, the speed, but maybe you should also mention these, right? The discs. The 140-year-old invention that FLL started, late 19th century. And for the first time, or second time, we make them plastic, right? So this is how we convert this into a football field without actually making it bigger.
That's true. Yeah, each one of these represents an equivalent surface area, and you start to stack them up, you can see It maybe only takes 1 or 2 of these in order to equal the surface area that we have here.
Yeah.
And in this case, just 1 of these discs exceeds the surface area that we have at work for us over on the taller system. So right away, if I start to take and stack these all up and get into 10s or more of them, now I've got something with a lot more surface area and the speed, and that's where, that's where we get back to our football field.
Do you know how many discs we have in here?
Yes, I do.
Bet you do. Okay. So the thing is, we have separation going on, and we said that we can get it clarified. It'll take longer here. But the second thing that you would like to talk about is, why is it better when you can have this increased G-force, so you can really squeeze them or push them against the periphery, you can squeeze the cells dry.
I agree. And that's kind of a secondary benefit. We talk about increasing the surface area, and you're not the only one who brings the visual aids. I have one of my favorite.
You cut it nicely, also. Yes.
Yeah, one of my favorite parlor tricks is right here. Right?
Do you do this for dinner parties?
Absolutely.
Oh, of course you do.
Yeah. But now that you've seen it here, perhaps you're not interested past this. But in any event, one of the other benefits that you have is we have a system which is rotating, which really has the effect of squeezing the material.
Right.
Most filtration systems, they operate at a differential pressure of about 2 bar. But here we have several hundred times that working for us. The material's under compression to a lot higher degree. So if we think of this as a 2-phase system, and we are interested in making the best possible separation between the water and the sponge, and we can say that the sponge represents the biomass, the spent biomass, and the water represents the product-rich liquid that's going to go downstream, and that's where you're going to get your soluble proteins eventually out of the material. If I don't make a good, clean separation here, I lose a lot of one phase or the other, which represents a big yield hit. And because this is the first separation stage in the product recovery effort, anything that we lose in the separation here has a big effect on the total yield on the process.
Yeah.
So let's look at this and think about it a little bit. If I reach in and make a very simple separation just by picking the sponge up, you can see as
you lost a lot of liquid.
It's dripping a little bit, and when we know that the sponge is full of liquid, let's give it a squeeze, and we'll see just how much liquid we would have lost if that was the extent of how we performed the separation. If,
like,
however,
100 milliliters.
That's a good percentage of what we have in here.
Yep.
If, however, I squeeze the sponge down below the liquid level before I remove it from the system, now I have a very dry sponge, and I have made a very clean separation, which means that
it's not the sponge that's right. It's that you keep the liquid in here. So
exactly. Right. So we've made a good clean separation and retained a lot of the liquid where we want it for the downstream processing. So in a sedimentation device like you have here, you're able to remove the biomass under compression in the system. So it's one thing to have it enhance the separation area. It's another thing to pull the materials away from each other under compression. So by compressing our sponge and removing all of the liquid from the sponge, before we remove it from the system, we maximize the yield of the liquid phase.
But that makes me wonder, when we were first trying this out, we had the heavy phase, the cells, flowing out through this tube into a 50-liter bag. Do you think anybody had ever seen so many CHO cells at that high concentration before? I mean, where could you get that before you had a separator?
No, I think it was something new for us to see, and some of our customers to see.
I think we were lucky because we saw that they were actually flow. It's like what we call the angle of repose was very low, right? So they were like flowing as a custard or something.
Yeah, about like that. Yeah.
So that was very lucky. Maybe if the pharma industry would have used some other vector for making the drugs that would not flow as easily, this would have been much more difficult to make.
I mean, that's true, right? There has, over the years, been a number of different host organisms. Many years ago, everything was a chemical formulation. Then things were moved to a yeast-based platform, then to E. coli. And the latest is of course, cell culture-based products, where that's, the vast majority of new drug products and the vast majority of commercialized products are made in a cell culture type of a host organism.
So I think E. coli, they're pretty small and hard and easy to separate, right? But like yeast or something which is more fluffy, that would have made our life much harder to get it through here, because we can't use pressure. We want to keep the cells intact. So when they're coming through the pumps and through here and out, we want to make sure that they're not stressed. There's no shear stress or anything else working on them.
Yeah, I think you can utilize something like this for different host cell organisms, but knowing that a lot of things are done in cell culture, I think that had a lot to do with the design effort that your team made to come up with something which would be optimized for what is the majority of products that have been commercialized.
Yeah. My favorite stuff. Can I just mention it?
I can't ever stop you from playing with your toys, Pontus. So you go right ahead.
That's why we, R&D, we like to invent and think about new stuff all the time, and then it's your job to make sure that we're directed somewhere, right? So that whatever we think of is useful. But I think this is useful for us because we need to understand how things are transported. What's the mechanical property of a cell suspension? We think that's interesting, and Alfa Laval, as separator makers, think that's interesting, but we need to sometimes explain to customers that just because it's CHO cells or E. coli or whatever, it's not always the same. Some cell soups are easy to separate because they're viable, they're all intact, like, they can flow like this. But if they've been standing for too long and they're not happy, their viability is like 30%. We had this happen, right? I came back from vacation and this customer is calling like, we can't separate it, what's wrong? It's something that's wrong with your machine. And then we, after a couple of hours, understand, what's the viability of your CHO cell suspension? And it was down to I think 35%. Well, obviously then half of these cells are broken and now they don't flow. So it's important for us to explain also what are the limitations to using this device. The operating conditions that you described, they are going to be different, from one customer to the next, or one location to the next, and even within the same product, one day to the next. Knowing that, and knowing that we have the capability to operate with a wide variety of conditions on the inlet side and still affect the most that can be done is an interesting part of the fact that we deal with a single stream in and two streams out on a continuous basis. And that's different than what you find with most filtration setups, is they are limited by a certain capacity per unit area, number one. And number two, if you have to switch them backwards and forwards, back flushing and to try to keep the filters clean and so forth and so on, they end up taking longer time to process, not doing an even job. Here we get the one stream in and the two streams out. It's kind of a set it and forget it type of an arrangement. So versatility, I think, is a lot different, even if you run into the tough circumstances that you describe. Okay, but let's get back there. So we're saying this is a really good device for sort of high titers or high cell concentration, right? But we're also replacing. There's like this elephant in the room here. At least when I talk to my friends and my family, sit around. I don't do this trick, I don't know what your friends think when you bring this up, but I'm sure they're very happy, right?
It depends on the crowd, but okay.
Yeah, okay. Do you do it in beer or water?
What's that?
You do it in beer?
I would never waste good beer.
Oh, no. Good. But my issue, when I talk about making things in plastic, people are like, that's not sustainable. That's not a good path going forward. Why you should just tell them to buy a stainless steel separator instead. And maybe, I mean, the customers that we're talking to, they're used to it, and they save, the plastic consumption goes down, because instead of having a filter stack this high, you get 2.5 kilos, right? So you actually get less waste using this.
That's true. I mean, the savings for the capability of this device at 2.5 kilos, the equivalent filtration system would be 20 times or more,
right?
In the plastic waste.
Yeah.
So, yes, it is plastic, but it is orders of magnitude better than the alternative filtration system.
Right. So I've told my especially my sister-in-law, that if you buy this, if you use a filter, you have to fill it up with water, right? You have to get all that extra waste. So that's not very good, because then you have more waste. If you use a stainless steel separator, now you have to clean it instead. You have to clean it, sterilize it, chemicals, energy, water. That's not good either, of course. It is good if you run big batches for a long time. The cleaning becomes less and less per produced volume.
Well, the argument of stainless steel systems versus single-use type of systems, that from a sustainability point of view, that's an apples and oranges discussion. Right. And you're going to get different opinions with regard to what is worse.
Yeah.
A bunch of chemicals and water that has to be disposed of, or plastics that are used just the one time as consumable parts of a process system. But within the single-use environment, I think that we can be very confident in terms of the savings of plastics in a separator device versus a filter.
Yeah, because also you just have the fact that in the filter you get all your cells stuck in the filter, so it's more just the weight of handling it is higher. It's worse for just carrying stuff around. Whereas in this one you get everything in either your drain or a bag or wherever you want it.
Well, that's true. Both the dry weight waste and the wet weight waste, if you will, is a lot less when you go to a device like this.
Yeah, and this, it sounds obvious, but it's important. I mean, like when you're hiring people, they want to feel that they're doing something that's good for the environment, good for sustainability, and that's why I just want to touch base on that also. So,
Pontus, in the last 5 years, we've come a long way together.
Yes.
It's been a fantastic journey in terms of translating, an old technology into a completely new format.
Yeah.
And I think that, in talking to people about how it's, provided them the possibilities to do things that they couldn't do five years ago. We've gotten a lot of positive feedback, and the sustainability improvements, have been acknowledged as well. I couldn't be happier with the result for the last 5 years.
This has been really an amazing journey. I think we've had a great team. We made a super interesting product. And the way I like to look at it is like we're actually helping the world to produce cheaper or lower the cost, at least, of the manufacturing cost of drugs.
Well, the efficiency improvements, you're right. They can free up more time in these facilities to perhaps make an additional batch, perhaps be more efficient, perhaps lower the cost.
Right.
All of these things are in play in terms of providing better accessibility for the products that our customers are making to help people all over the world.
Yeah. Thank you for being here.
It's been fun. Now I do wish this were beer.
Yeah. Or something.